Welcome to Math Tutorials. In this video, we are solving every question of exercise 6.3 of Chapter 6, Applications of Derivatives, from the NCERT Mathematics textbook for Class 12, Part 1. Exercise 6.3 is the heart of the chapter. 29 questions on maxima and minima, from reading extremes off completed squares through first and second derivative tests, to the classic optimization problems of boxes, cans, wires, cones, and spheres, ending with 3 multiple choice. Here is the full list. Question 1. 4 functions whose extreme values can be read off by completing squares, without any calculus. Squares are never negative. That single fact settles the first 3. Part 1, the square is at least 0, so f is at least 3, attained at x equals 1/2. No maximum, the square grows without bound. Part 2, complete the square as 3x plus 2 squared minus 2. Minimum minus 2, at x equals minus 2/3, no maximum. Part 3, the negated square makes 10 a maximum at x equals 1, with no minimum. Part 4, the cube runs from minus infinity to infinity, so g has neither a maximum nor a minimum. Question 2. 5 more, now with moduli, signs, and an open interval trap at the end. Moduli are at least 0, signs live between -1 and 1. Part 1, the modulus is at least 0, so minimum -1 at x equals -2, no maximum. Part 2, flipped, maximum 3 at -1, no minimum. Part 3, sine 2x spans -1 to 1, so h spans 4 to 6, both attained. Part 4, sine 4x plus 3 stays between 2 and 4, already positive, so the modulus changes nothing. Maximum 4, minimum 2. Part 5, on the open interval the endpoints 0 and 2 are approached but never reached. Neither a maximum nor a minimum exists. Question 3. 8 local extremum hunts, critical points from the first derivative, verdicts from the second. We go part by part. Each takes 1 critical point computation and 1 test. Part 1, derivative 2x vanishes at 0, second derivative positive. Local minimum 0. Part 2, critical points plus and -1 give a local max 2 at -1 and a local min -2 at 1. Part 3, cosine minus sine vanishes at pi/4, second derivative negative. Local maximum root 2. Part 4, cosine plus sine vanishes at 3 pi/4 and 7 pi/4. A local maximum root 2 at the first, a local minimum minus root 2 at the second. Part 5, the derivative factors as 3x minus 1x minus 3. Local maximum 19 at 1, local minimum 15 at 3. Part 6, 1/2 minus 2 over x squared vanishes at x equals 2, second derivative positive, local minimum 2. Part 7, the derivative is negative x over a square, 0 only at 0, local maximum 1/2. Part 8, the derivative combines to 2 minus 3x over twice the root, vanishing at 2/3. A local maximum with value 2 root 3 over 9. Question 4. 3 functions that never turn, their derivatives never vanish. No critical point, no extremum. Part 1, the derivative e to the x is strictly positive everywhere, never 0. Part 2, 1 over x is also positive on the whole domain. Part 3, the quadratic derivative has negative discriminant, 4 minus 12, so it has no real root and stays positive. With strictly monotone behavior and no critical points, none of the 3 has any maximum or minimum. Question 5. Absolute extrema on closed intervals. Compare critical values with endpoint values. 4 short comparisons. Part 1, x cubed is increasing, so the endpoints give everything. Maximum 8 at 2, minimum -8 at -2. Part 2, the critical point pi over 4 gives root 2, endpoints give 1 and minus 1. Maximum root 2, minimum minus 1. Part 3, derivative 4 minus x vanishes at 4, giving 8. The endpoints give minus 10 and 63 over 8. Maximum 8 at 4, minimum minus 10 at minus 2. Part 4, the vertex x equals 1 is an endpoint here, value 3, the far endpoint gives 19. Maximum 19, minimum 3. Question 6. A downward parabola of profit, 1 critical point, 1 second derivative check. Set the derivative to 0. X equals minus 2, and the second derivative minus 36 confirms a maximum. The maximum profit is P at minus 2. 41 plus 144 minus 72, which is 113. Question 7. A quartic on a closed interval. The derivative factors, with a quadratic that never vanishes. Differentiate and factor. Only x equals 2 is a real critical point. Evaluate at the critical point and both endpoints. Maximum 25 at 0, minimum minus 39 at 2. Question 8. Sine of 2x completes 2 full waves on the interval, so the peak is hit twice. Set the inner angle to pi over 2 plus full turns. The maximum value 1 occurs when 2x is pi over 2 or 5 pi over 2 within range. Question 9. The classic sum of sine and cosine. Rewrite as a single sine, with amplitude root 2. The combination is root 2 times sine of x plus pi over 4, whose peak is root 2. Question 10. 1 cubic, 2 intervals, 2 answers. The critical points are at plus and minus 2, 1 inside each interval. The derivative vanishes at plus and minus 2. On 1 to 3, compare f at 1, 2, 3, values 85, 75, 89. Maximum 89 at x equals 3. On minus 3 to minus 1, values 125, 139, 129 at minus 3, minus 2, minus 1. Maximum 139 at x equals minus 2. Question 11. The parameter A must place the maximum exactly at x equals 1. An interior maximum forces the derivative to vanish there. Since 1 is interior to the interval, f prime of 1 must be 0. Solve A equals 120. Question 12. A rising line with a wiggle riding on it. The critical values stay strictly between the endpoint values, so the endpoints win. The derivative 1 plus 2 cosine 2x vanishes where cosine 2x is minus 1/2. 4 interior points. All 4 critical values lie strictly between the endpoint values 0 and 2 pi, so the absolute extremes sit at the endpoints. Question 13. Split 24 into 2 parts with the biggest product. Write the product as a function of one part. With parts x and 24 minus x, the product is a downward parabola. Its derivative vanishes at 12. Second derivative minus 2 confirms the maximum. Both numbers 12, product 144. Question 14. 60 split so that x times y cubed peaks. Eliminate x and differentiate in y. Substitute x equals 60 minus y and differentiate the quartic. The positive critical point is y equals 45, a maximum by the sign change. Then x is 15. Question 15. The same game with exponents 2 and 5. The peak splits the sum in the ratio of the exponents. With x equals 35 minus y, differentiate and factor. The interior critical point is y equals 25, so x is 10, the ratio 2 to 5 of the exponents. Question 16. 16 split to make the cubes together as small as possible. Symmetry suggests the middle. Calculus confirms it. With parts x and 16 minus x, differentiate the sum of cubes. Setting it to 0 forces x equals 16 minus x, so x is 8. The second derivative 96 is positive. A minimum. Both numbers are 8. Question 17. The classic box problem. Cut corners of side x from an 18 centimeter square and fold. Volume is x times the shrunken base squared. The base becomes 18 minus 2x on each side, with height x. Differentiate with the product rule and factor. The zeros are 9, which kills the box, and 3. The second derivative test or sign chart confirms 3 is the maximum. Question 18. The rectangular version, 45 by 24. Same setup, a quadratic to factor at the end. The volume with corner x. Differentiate and factor. X equals 18 is impossible since 24 minus 36 is negative. X equals 5 is the maximum, confirmed by the negative second derivative there. Question 19. All rectangles in one circle, the square must win. The diagonal of any inscribed rectangle is the diameter. With radius and sides x and y, the diagonal is the diameter. X squared plus y squared equals 4 squared. Maximize the squared area to avoid roots. A squared as a function of x squared is a downward parabola. The critical point is x squared equals 2 squared, and then y squared matches. X equals y. The rectangle of maximum area is the square. Question 20. Fixed total surface, biggest cylinder. The claim is height equals diameter. Eliminate the height with the surface constraint. The surface constraint solves for h. Substitute into the volume. V becomes a cubic in r. Differentiate and set to 0. S equals 6 pi r squared. The second derivative minus 6 pi r is negative, a maximum. Feed that s back into the constraint. 6 pi r squared equals 2 pi r squared plus 2 pi r h, so h equals 2r, the diameter. Question 21. A 100 cubic centimeter can with the least metal. Eliminate h with the volume, minimize the surface. The volume fixes h in terms of r. The surface becomes a function of r alone. Differentiate and set to 0. R cubed is 50 over pi, the second derivative is positive there, a minimum. Then h is 100 over pi r squared, which is exactly 2r. The can is as tall as it is wide. Question 22. 28 meters of wire, split between a square and a circle, minimizing total area. Express both areas in the squares share x. A piece x makes a square of side x over 4. The rest makes a circle of radius 28 minus x over 2 pi. Differentiate and set to 0. Solve. The square gets 112 over pi plus 4 meters. The circle the remaining 28 pi over pi plus 4. The positive second derivative makes it a minimum. Question 23. The biggest cone inside a sphere. Exactly 8/27 of the sphere. Write the cone's base radius in terms of its height via the sphere. A cone of height h has its base circle at distance h minus r from the center. So the base radius obeys r squared equals 2rh minus h squared. The volume becomes a cubic in h. Differentiate, the maximum sits at h equals 4/3 r. Substitute back. The volume is 32 pi r cubed over 81, which is exactly 8/27 of the sphere's 4/3 pi r cubed. Question 24. Fixed volume, least lateral surface, height root 2 times radius. Work with the squared surface to dodge the square root. The volume constraint fixes r squared h as a constant k. The curved surface squared is pi squared r squared times r squared plus h squared. Substitute h equals k over r squared. Differentiate in r and set to 0. 2r to the 6th equals k squared, that is r to the 6th equals r to the 4th h squared over 2, giving h squared equals 2r squared. So the altitude is root 2 times the base radius, and the sign of the derivative confirms the minimum. Question 25. Fix slant height, biggest volume. The half angle is inverse tangent of root 2. Express the volume in the height using the slant relation. With slant L, the base radius obeys r squared equals L squared minus h squared, so the volume is a cubic in h. Differentiate, the maximum is at h equals L over root 3. Then r squared is 2/3 L squared, and tangent of the half angle r over h is root 2. The semi-vertical angle is inverse tangent root 2. Question 26. Fix total surface now, and the answer is inverse sine of 1/3. The total surface pi rl plus pi r squared is the constraint. From the fixed surface S equals pi rl plus pi r squared, solve for the slant L. Square the volume and substitute h squared equals L squared minus r squared. V squared simplifies to a function whose derivative vanishes when S equals 4 pi r squared. Then pi rl equals S minus pi r squared equals 3 pi r squared, so L equals 3r, and sine of the semi-vertical angle r over L is 1/3. Question 27, multiple choice. The closest point of a parabola to the point 0, 5. Minimize the squared distance, using the curve to eliminate x. On the curve x squared is 2y, so the squared distance to 0, 5 becomes a function of y alone. Differentiate, y equals 4 and then x is 2 root 2. Option A. Question 28, multiple choice. A ratio of two quadratics that never vanish. The quotient rule numerator collapses to 2x squared minus 2. Differentiate. The numerator of f prime reduces to 2 times x squared minus 1, so the critical points are plus and minus 1. Evaluate, f of 1 is 1/3, f of minus 1 is 3. The minimum is 1/3, option D. Question 29, the last one, multiple choice. A cube root of a quadratic on the unit interval. The cube root is increasing, so maximize the inside. The inside x squared minus x plus 1 has its vertex minimum 3/4 at 1/2, and takes the value 1 at both endpoints. So the maximum of the inside is 1, and the cube root of 1 is 1. Option C. That completes all 29 questions of exercise 6.3. In the next video, we will take up the miscellaneous exercise on Chapter 6, the final video of Part 1. Thank you for watching. If you found this video helpful, do like it, subscribe to math tutorials, and share it with your friends.